You guys have been looking at the roots of quadratic equations for a little bit now. Now what we're going to do is figure out a way that we can determine what the nature of those roots are. And the way that we do that is with the discriminant. It's actually the part of the quadratic formula that's that's underneath the radical. Usually we call it d, so it's actually equal to b squared minus 4ac. The mistake that most people make is they think the discriminant is also the square root applied. You actually do not take the square root of this number. The discriminant is just what's underneath the radical. So if you look at R1 and R2 here, those are the two roots of the quadratic. So we have negative b plus the square root of the discriminant, or b squared minus 4ac, over 2a. And the second root is negative b minus all of that. So anytime you do the quadratic formula and you write that plus or minus, you're really looking for two values, the one where you add, the one where you subtract. So now what we'll do is we will calculate the discriminant for each of these, and then we'll calculate the root. So first the discriminant, which is b squared minus 4ac. So that's negative 8 squared minus 4 times 1 times 5. And this gives us a discriminant of 44. So when we're calculating our roots, it's negative b plus the square root of the discriminant over 2 and negative b minus the square root of the discriminant over 2. We should be able to recognize that 44 is not a perfect square, so our two roots are going to be 8 plus 2 square root 11, because remember 44 is 4 times 11, I can pull that out from under the radical, over 2, and 8 minus 2 square root 11 over 2. And then I could factor out a 2 and cancel. So my two roots are 4 plus or minus the square root of 11. Let's take a look at the next problem. We'll calculate the discriminant first. And that's b squared minus 4ac. Well, 10 squared is 100, and 4 times 25 is 100, so in this case, the discriminant is 0. So if I start looking at the roots, it's negative b plus the square root of 0 over 2, and negative b minus the square root of 0 over 2. The square root of 0 is just 0, and the negative 10 over 2 would be 5. So x sub 1 would be negative 5, and x sub 2 would also be negative 5. So in this case, we have a double root. The only root of this quadratic is negative 5. We're going to continue to work on this. Here's the discriminant. It's b squared minus 4ac. So this is 16 minus 52, which gives us negative 36. That's what will go under the radical. So when we look at our roots, we have negative b plus the square root of negative 36 over 2, and negative b minus the square root, that's a 36 by the way, of negative 36 over 2. So this becomes 4 plus 6i over 2, and 4 minus 6i over 2 I can simplify those. And I get that my two roots are 2 plus or minus 3i. So in this case, I have imaginary roots. On the next problem, this should say that it's equal to 0, and then we would proceed with the discriminant. When I simplify this, I get 49 ninths minus 8 thirds, and if I multiply that by 3 over 3, then I would get 24 ninths. So 49 ninths minus 24 ninths will actually give me 25 ninths. So if I do negative b plus the square root of 25 ninths over 2 and negative b minus the square root of 25 ninths over 2, this becomes negative 7 thirds plus 5 thirds, so that gives me negative 2 thirds, over 2. And x sub 2 would give me negative 12 thirds over 2. When I copy dot flop this first one, I get that x sub 1 is equal to negative 1 third. And when I simplify x sub 2, I get negative 2. Let's take a look at the next one. Okay, taking a look at the last one, there should be an x here. That's 4 square root of 2x. Calculating the discriminant, that's b squared, so 4 root 2 squared minus 4 times 1 times negative 8. 4 root 2 squared, that's 16 times 2, which is 32. And then negative 4 times negative 8 is 32, so that actually gives us 64 as the discriminant. So I have negative b plus the square root of 64 over 2 and negative b minus the square root of 64 over 2. So this will give us and then of course we can simplify. This cancel, we get a 4 and a 2. Same thing here. So x sub 1 is negative 2 root 2 plus 4, and x sub 2 is negative 2 root 2 minus 4. So what we just did with all those discriminants is determine the nature of the roots of a quadratic equation. So we're saying, okay, here's our quadratic and our coefficients are real numbers. If our discriminant is a positive number, okay, positive number greater than 0, then we have two roots that are not equal to each other. If our discriminant is exactly 0, then we have one root that's a double root. That's the one that we did one example of, and the root was negative 5. If your discriminant is negative, then your roots are imaginary conjugates. To know if your roots are rational or not, right? The last one, 2 root 2 plus 2, not rational. But the one before that, where it was like negative a third and negative 2, those are rational. So to test if your roots are rational, first of all, the quadratic has to have integer coefficients. and the discriminant has to be a perfect square. If you can transform it into this sort of thing where coefficients are integers and the discriminants are perfect squares, then the roots will also be rational. The reason that we even care about discriminant is because it can actually help us determine which is the most efficient way to solve the quadratic. So if your discriminant is a perfect square, then you want to factor, because factoring is going to be the easiest way to do this. If your equation has the form where this b term is an even number, then completing the square is probably the most efficient. You can always use quadratic formula, but you have to understand that sometimes it might actually take more time to do that than one of these other two methods. If your discriminant is greater than or equal to 0, you can always graph it. But this will not work if your roots are imaginary. Imaginary roots, you will need to use one of those other methods. Also, if those roots are irrational, then you will get an estimated answer rather than an exact answer, which is probably not going to be the best option for you. All right, so let's take a look at some word problems, all of your favorite. We've got the volume of a jewelry box that's 4 centimeters in height, and the volume is 136 cubic centimeters. The perimeter of the base is 24 centimeters. We need to find the dimensions of the base. So, a couple things we need to remember: that the perimeter of the base is going to be 2 times the length plus 2 times the width, and that the volume is length times width times height. Now, what I would do is I would set that perimeter equal to 24, which is what they told me, and I would solve for either L or W. I'm actually going to solve for L. So when I look at the volume formula, I'll be able to replace L with 12 minus W, and I already know that I can replace H with 4. So 136 is equal to 12 minus W times 4W. From here, I will expand this into a quadratic, and what I get is 4W squared minus 48W plus 136 is equal to 0. From here, I see that I can factor out a 4. And what I'll do next, before I figure out how I want to go about solving this, is I will calculate the discriminant. So that's b squared minus 4 times 1 times 34. And this discriminant is 8. This is not a perfect square, but it's not negative, so I'm going to have a real root, but it won't be rational. Based on what I'm seeing here, because I have this even number in the middle, I'm going to complete the square in order to solve this. So I will complete the square on W squared minus 12W plus 34 equals 0. So remember, when you complete the square, we'll bring 34 over. And that actually becomes a negative 34. Cut the 12 in half, we get 6. Square that, we get 36. So we add that to both sides of the equation. Take the square root of both sides. And add 6. So the dimensions of the base here are 6 plus the square root of 2 and 6 minus the square root of 2. You can put those into your calculator and get decimal approximations for it. All right, the next problem, we have a 5 by 7 inch picture surrounded by a frame of uniform width. The area of the frame equals the area of the photograph. Find the width of the frame. To do this problem, you sort of have to know what you're looking at. So we've got this frame with a picture in it, and the picture is 5 by 7. And this is x, and this distance is x, and this distance is x. So when you're looking at the whole bottom here, you've got 5 and 2x. And then the same thing when you're looking at this whole distance, you have 7 plus x plus x. So we know the area of the picture in here is 35 because that's 5 times 7. So the way that we set this up is we say, okay, well, we've got 5 plus 2x times 7 plus 2x, but we're actually going to subtract out this hole that the picture goes in because that's not part of the frame. Only this stuff in here is part of the frame. So we'll subtract out the 35, but that whole thing is actually equal to the area of the picture, which is 35. When we factor all of this, we end up with 4x squared plus 24x minus 35 is equal to 0. So I factored and I just rearranged everything to set it equal to 0. I then look at my discriminant, which is b squared minus 4ac, so that's 24 squared minus 4 times negative 35. And for this, I get a discriminant of 1,136. This is not a perfect square, so I don't really want to factor. I suppose I could complete the square because this is even, but since I have an a term here and this isn't divisible by 4, I kind of don't want to deal with completing the square. So in this problem, I'm actually just going to use quadratic formula. So that's negative b plus or minus the square root of the discriminant over 2a, which in this case is 8. Now, 1,136 is 16 times 71. And then I can reduce this. Everything's divisible by 4, so this becomes a 2. This goes away, and then 24 divided by 4 is 6. And I guess I should have written that better. This whole thing is divided by 2. And from here, because it's a word problem, you would put these numbers into your calculator, and you probably would not use the one that's negative. You would only use the positive values of this. And of course, for both of these, you would write your sentence as well. All right, so we have a box with a square base and no lid, and we're going to make it from a square piece of metal, and we're going to cut some squares out of the corners and fold up the sides. So here's what that original thing looks like. There's your original square piece of metal, and you're going to cut these corners here, and then you'll fold up these sides to form a box. And it says that the cutoff squares are 5 centimeters on each side. Here's what your box is going to look like. Here's that 5 centimeters, is these is now the height. And so this dimension here is x, because we don't know what it is. That actually shows up here in the middle. These are all x. So our whole length is 5 plus x plus 5. So that becomes 10 plus x. And then this distance is 5 plus x plus 5. So that's also 10 plus x. Now, we're told that the volume is 100 cubic centimeters. So length times width times height is 100. So length is x, width is x, height is 5. So 5x squared is equal to 100. This is actually a pretty simple problem now. 100 divided by 5 is 20. And then, of course, we take the square root of both sides and we get plus or minus 2 square roots of 5 is equal to x. And so now what they're saying is we actually want the dimensions of this original piece of metal. So we need 10 plus x. It cannot be less than 10 because we have to cut 5 out of it, which means that this negative won't work. So the dimensions of the original piece of metal will be 10 plus 2 square roots of 5. You will plug this into your calculator, you will come up with an estimated decimal value, and you will write the original piece of metal has dimensions of whatever this value happens to be. This last section is dealing with equations in quadratic forms and the way that we can actually transform equations so that they look like the quadratics we are used to seeing. You will know that an equation is in quadratic form. For example, if you have something like this under the radical and the same value not, okay? Because essentially under the radical is the same squared is this. So that's sort of what you're going to look for. Just like the last time, this was like x to the 4th and this one was x squared. That was still quadratic form. The way that you're going to attack these problems is with a different letter that we'll use. So here I'll say, let's let a equal to the square root of x. Well, if I square that, if I do a squared is equal to just square root of x squared, which is x. So when I do that, this equation becomes a squared minus 5a plus 6 is equal to 0. This is something that we're really familiar with and really comfortable with. We can even factor it. So a is equal to 2 or 3. The place where so many students make mistakes is not following through the problem. So now I come back up here and I say, well, 2 is equal to the square root of x and 3 is equal to the square root of x. Well, if I square x, or if I square these in both equations, the squares will cancel the square root and I get that x is equal to 4 or 9. Let's take a look at the next one. If you don't like A, you don't have to use A, but be careful using B because a lot of your B's look like the number 6. So this next one is B squared plus 2B minus 15. Again, this problem becomes very, very simple. We can even factor it. So B is equal to negative 5 or 3. And again, this is where you'll make your mistake by not continuing into the problem. So if negative 5 has to equal the square root of 2x, and 3 has to equal the square root of 2x. Well, we're not going to take the square root of anything and get a negative number, so here, no solution. But on the other side, we can square both sides. We get that 9 is equal to 2x, and therefore x is equal to 9/2. Last problem. This one we really hate because not only are things not in the right place, but we've also got fractions to deal with. But we can still manage this. I'm going to go back to the letter A, and I'm going to let A equal 1 over the square root of u. Because if I square that, A squared is 1 over u. Which then means this becomes 6 times 1 over u, or 6 times A. 6a squared. And then this middle one becomes 17 times A. I will bring 5 over to the other side. And again, it's simple enough that I can factor it. And that means that A is equal to 1/3, or A is equal to 5/2. So again, I then can say, well, 1/3 has to equal 1 over the square root of u. If I cross multiply this, I get square root of u is equal to 3. Square both sides, u is equal to 9. I also have that 5/2 is equal to 1 over the square root of u. Again, cross multiply, or essentially I'm taking the reciprocal of both sides. The square root of u is equal to 2/5. Square both sides, u is equal to 4/25.